Okay. Hi everyone. So this is the paper presentation that I have selected, and the paper title is Transport Layer Obscurity, Circumventing SNI Censorship on the TLS Layer. And so the problem statement for this paper is TLS server name indication um, is sent in plain text during the handshake process and then exposing the destination host name. And the second one is censors and DPI systems exploit this to block access to domains content is encrypted, but the name is visible. And then traditional circumvention often works at TCP or application layers, not inside the TLS. So why it matters the most is blocking based on SNI undermines encrypted web access and user privacy, as TLS is ubiquitous for HTTPS. Solving SNI leakage has broad impact for censorship resistance. And then the key hypothesis and the approach overview is the hypothesis is that the TLS protocol itself includes internal handshake behaviors like fragmentation, extension ordering, padding, and then optional extensions that can be manipulated to obscure or hide SNI from sensors, and then while still satisfying servers and network infrastructure. And the approach for this is design and test TLS layer censorship circumvention techniques, not required changes to TCP or application, manipulate record fragmentation, reordering, handshake extension structure, and optional or unencrypted fields, etc. And then test on real servers, CDNS, and or censorship middle boxes to see which techniques succeed or fail. And then the technical techniques, for example, show the standard TLS handshake and then highlight where techniques intervene. Examples of techniques, from the paper are like record fragmentation or splitting. Break the client hello or extensions across multiple TLS records to hide SNI in non obvious segments. And then extension reordering or padding or filter bytes. For example, reorder or pad extension fields so that SNI is less deterministic in location. And the third one is using optional or experimentally unencrypted extensions to mask or shift offsets. And then interplay with encrypted client hello ECH features if supported, if applicable, to reduce reliance on plain text SNI. And then emphasize constants are like they must still be accepted by real servers and not immediately rejected by middle boxes. And then evaluation setup is like outline the empirical evaluation methodology, a catalog of 38 candidate techniques grouped into 11 categories, tested for acceptance, and then testing against a major TLS servers or CDNs or popular hosting setups. In the wild experiments, simulating censorship in China or Iran to see real world behavior. Metrics are like success or failure, drop rate by middle boxes, compatibility, false negatives. Also, detection of censorship architecture is that the authors identify at least three distinct censorship appliances in China. And then evaluation results and findings are um, a bar chart or table summarizing how many techniques succeeded versus failed per server CDN categories. So the key empirical highlights are many techniques do succeed in circumventing SNI blocking in real settings. Some techniques fail due to the middle box strictness or non-tolerance of anomaly in handshake structuring. The diversity of sensor devices are different appliances in China handle TLS differently. So no one technique is universally effective. Uh, and a note is that the work reveals fragile circumvention surfaces and emphasizes importance of cross-layer fingerprinting. And then new insights and contributions are like TLS is not just a passive victim of censorship. Its handshake structure is a rich surface of evasion. And then the paper expands the space of censorship circumvention for network and transport layers into the cryptographic protocol itself. Sensors are not monolithic. Different devices may parse or enforce TLS differently, which gives room for selective evasion. And then encrypted client hello, ECH, and future TLS enhancements matters, but deployment is uneven and sensors may adapt. The paper also provides a categorized library of techniques and failure modes for future researchers to build on. And then implications, limitations, and future works are implications include developers of VPNs, censorship resistance tools, TLS libraries should consider integrating some of these techniques. And then standard bodies like TLSWG should consider how handshake flexibility, extension encryption, and features evolve to resist censorship. Limitations are that not all techniques succeed everywhere, maybe little in presence of exotic middle boxes. Some techniques rely on behaviors that might be flagged or blocked as anomalies in future updates. Deployment of ECH or TLS uh, evaluation lags behind sensor adaptation. And then the future directions, automated synthesis or evaluation of new TLS level evasion strategies, better integration with ECH or hybrid schemes, and then measuring how sensors respond over time. The arms race. And then the broader impact of how the world looks different is because of this work, the research community now views the TLS handshake itself as an active place to counter censorship. Tools and systems can increasingly embed TLS layer evasion, not just proxying about TCP. The arm race intensifies, sensors may respond by stricter TLS parsing, anomaly detection, or disabling flexibility. And then in summary, the problem is that plain text SNI in TLS handshake enables censorship. Approach is that manipulate handshake semantics to obscure SNI, and then result is that many techniques succeed, but challenges remain. Insight is that TLS is both threat and opportunity. Future work must bridge protocol design, deployment, and sensor behavior. And then these are the references that I have taken. Uh, Thank you.